part 2 of our forces and Newton's 3 laws notes, and we're focusing on what you can see here called friction. All right, what is this unbalanced force that acts on an object in motion? And that is friction. There are 4 major types of friction. There is sliding friction, rolling friction, fluid friction, which is usually air or liquid. We tend to say fluid as water, but air is also a fluid, Newtonian fluid. And then static friction. This is the initial friction when moving an object. Static friction is why things don't just slide off the table or your butt slides out of a chair, okay, because of this whole idea of static friction. Newton's second law with friction. Friction, forces that opposes motion between 2 surfaces that are touching. If the surfaces aren't touching, there cannot be friction. Microwelds. Microwelds are areas of surface that stick together. Okay, microwelds are like little itty bitty, kind of almost think of it like Velcro. Okay, friction between 2 surfaces that are not moving past each other is called static friction again. Sliding friction is when forces slide past each other. And then friction between rolling object and a surface is called rolling friction. So microwelds, this is an old thing, but no matter how flat you think a surface is at the microscopic or submicroscopic or the atomic level, it's not smooth. There are tiny, tiny, tiny little things, okay, that are holding them together. So you got to think of it like little pieces of Velcro. If we smush more force, that Velcro is going to be tighter together and it's not going to move. Lightly, there's still a little bit. You can hear that Velcro kind of sliding past each other, but not too much. So again, microwelds, depending on the shape of the object and also depending upon the shape of the surface, there can be more or less microwelds. Okay, so with static friction, if you look here like a book sliding across the floor actually looks like this at the microscopic level, all jaggedy like a little mountain range. So when it goes over there, we know that static friction, there's got to be some force. A static friction will be more and more and more until the point where the book starts to move or the thing starts to move, and we're going to have a nice constant amount there. Okay, so sum of all the forces again. All right, if we look at the net force, all right, the net force, since the forces are all balanced, okay, if friction is less than the applied force, so if this is friction and this is the applied force, then we're going to have motion in that direction. Rolling friction, okay, rolling friction tends to be the most efficient, shall we say, least efficient friction, but most efficient for moving. And that's because there is only one point of contact. There's only one point of contact. So sometimes it packages, like you'll see packages moving on TV, like when they show delivery services and stuff, they're moving on these little tables that have a bunch of rollers, and it's really easy. You can barely touch that box and it's going to roll a long distance. That's why wheels are round, okay? Because there's only one point of contact. We're going to watch this little link here, this little video, and we'll come on back.
Curling has been in the Winter Olympics since 1998, but still seems a little strange to most of us. We had John Schuster, captain or skip of the U.S. curling team in Vancouver, explain this unusual sport for us, while scientists funded by the National Science Foundation explain how friction makes it all work. Curling, perhaps the most unusual sport in the Winter Olympics. A huge rock is thrust down a long sheet of ice. 2 players sweep a path in front of it, guiding it to the center of the target, called the house. At the end of play, the team with the most points, the most rocks closer to the center, wins. Olympic bronze medal winner John Schuster is a lifelong curler.
My family is big into curling. I remember throwing a rock at the curling club when I was, probably 6 or 8 years old.
Getting the curling stone from the start to the house is all physics, starting with a push-off against what's called the hack.
What you're able to do off of here is to position your foot to allow yourself to accelerate out of the hack with a curling rock. You can push out of this hack with a very high amount of force, and you know that it's going to transfer into the curling rock.
Then the sweepers move in.
This is like a synthetic material that has just a little bit of abrasiveness. Curling terminology as far as sweeping goes, it's anything that you could consider versions of yes. Yeah! But usually it's hurry and hard. You want them to push harder.
To help the stone go farther and straighter.
Back in the old days, people used to think when you swept in front of a rock, you cleared out snow and frost, and that allowed the rock to go further. Well, after we got the snow and frost elements removed when we moved indoors, all of a sudden you're sweeping a rock, and it's even affecting it more. It's going 15 feet further.
That's because sweeping wasn't just removing the snow and ice, it was reducing the friction between the stone and ice. The rapid back and forth of the sweeping generates heat.
It all just comes down to this, yeah. It comes down to this. They're warming that ice up, maybe enough to generate a meltwater film.
A meltwater layer that reduces friction creates a literal path of least resistance for the stone to glide on more easily. Friction is reduced even further by another characteristic of curling ice: bumps.
All the other ice sports have a smooth Zamboni surface, effectively. And curling requires that the surface of the ice be roughened.
Spraying water does the trick.
And then when it lands on the ice, it freezes up and forms these nice pebble-shaped bumps. And if you look at it, it looks like an orange peel. That kind of roughness is about the right texture. That gives us the surface we need.
But wouldn't the bumps, like mini speed bumps, just slow the stone down? Actually, it's the reverse. The points reduce the total ice surface the stone rides on. The less surface contact, the less friction. And there's another reason.
If we're on smooth, frozen Zamboni ice in an arena, if that's making a nice seal at the bottom of the stone, you're going to eventually form a vacuum as the stone moves across the ice, and it really slows it down. You've got air pressure pushing on the stone, whereas if you can have it riding on a few points, then it's going to slide more smoothly, and you won't get any kind of a vacuum forming, and it'll go roughly twice as far.
The makeup of the stone itself plays a role.
Curling rocks are 42 pounds of granite, and actually the granite only comes from the island called the Lisa Craig that's off the coast of Scotland.
This type of granite is hydrophobic. It resists water. That means it will absorb very little of the meltwater layer at the surface. Absorption could reduce the lubrication, helping the stone glide toward the house. As the curling stone approaches the target, there's a good chance another team stone is in the way. When the stones collide, another wonder of physics takes place: momentum exchange.
When you see the collision of two curling stones, you're seeing the transfer of kinetic energy between them, and you're also seeing the transfer of momentum, the product of mass and velocity between them.
Well, there you have it, the basic physics of curling. From the hack to the house, from the coefficient of friction to the transfer of kinetic energy, curling is a sport that attracts the crowds and delivers excitement with a bump.
All right. Oh, scared you again. Well, there you go. So again, a lot of stuff going on there. No biggie. Let's just talk about the math behind it. So this is what it's all about. So if we remember, then how do we calculate the force of friction? Well, you're going to have to follow along here. The force of friction, which is F sub F, okay, force of friction, is equal to mu, is what this is, mu K F of N, the normal force, okay? Well, mu K is the coefficient of friction, which is different for every object, okay? K means kinetic, which means things have to be moving, okay? So again, usually it's always going to be the kinetic coefficient of friction, all right? And then F of N, which is the normal force. And what normal force really means is F equals ma, force. So the force applied to some kind of friction will be the force of friction. Okay, so if we look at what we know that the net force is equal to the force applied minus the force of friction. That means the net force is equal to the force of flight. If we expand this, all we're doing is expanding this. All we're doing is changing the force of friction to this equation right here, which just came back from over here. So we're substituting force of friction. We're just expanding it. For you math people, this is a proof. Okay, we're expanding it. Then we're going to take this F of M, which is F equals ma, and we're going to expand it again to finally get this equation, which is the final equation, which is F of net equals the force applied minus the kinetic coefficient of friction times mass times acceleration. Okay, and we could expand this one more time. What's acceleration? Well, that's velocity divided by time. Okay, because if we know the velocity, we divide it by how much time times its mass, that's our force, times kinetic coefficient of friction, that's how much we have to subtract off the force applied to get our total net force. Again, we're going to do that. We're going to do a lab on this. Okay, if you're an RLA kid, we'll have that data for you. Maybe we'll have you log in. I don't know. We'll have to see what works out best for you. Okay, and then finally, we're going to have a review packet that you'll need to do, and that's all on your Schoology things. Okay, pretty simple, pretty normal. Again, make sure you rewatch this video, and if you have questions, make sure you get a hold of me. Otherwise, Mr. T.